You can put this right back into L2. You can overwrite our data. I'll slap it up on the screen. Here's the cumulative data, friends. Right here. I don't know if you can see it. It's right here. This includes you guys.
So is that our L2?
You can change this to L2. Change your L2 to these values right here. That's including you guys. I've got you guys, you updated. There's our curve. Look at that. Look at that freaking thing. Look where the average is. It's beautiful. So Renee, yes, there are some hiccups. There's also a hiccup here. Do you notice right there? And there's no hiccup here. These guys are almost perfect. I mean, perfect representative of that shape. But I love that you brought it up. But those random fluctuations have to happen, especially in somewhat small data sets. I mean, years ago, I tried to design an Excel spreadsheet that how many data points do you have to see until you recognize the shape of the data? And 16, this is, I think, getting at what Lauren's getting at is, you know, that might be an incomplete picture of a bell curve. So small, we can't call it a bell curve. But the idea is, it's demonstrating bell curve behavior, even with holes in it. I don't see that. I don't see a Weibull distribution or something like that, so good.
Does our L3 need to change?
If we want to compare it to that, yes ma'am, yes. I'm going to turn it off.
Oh, okay.
Kate asked a very good question. What our L3 have to change? Remember how we made L3 be L2 times 16? If you wanted to put that perfect curve up, we'd have to do L2 times whatever the sum of this is. We can do that if you want. What the hell? Let's do that too. So first things first. Don't worry, I'll walk you through it. Kate wants to compare the guessing curve to this curve. So we're going to update both graphs. So in L2, 0, 0, 3, 11, 14, 29, 29, 15, 8, 5, and 3. Now what Kate said is, I'd like to compare that to the perfect curve, which was in L3, but we're going to have to reconfigure L3. Oh, scheiße. We can be tricky about this.
It's not worth it. I don't care.
You sure? I'll do it up here, so we all have it together. Don't worry about it. I'm going to do it. You hush. There's the original values we had originally, right? So now we'll just do L4 times whatever that sums up to, which is a fun Excel trick. If you need a quick sum of numbers, just highlight them, and down here in the corner it tells you what they sum to if you ever need that. That comes in handy. You don't actually have to have the value in the spreadsheet. You can at least get how many items there are and what they sum to. Just
and the average.
And the average as well, exactly. Although that average doesn't tell us a whole lot of that column because it's frequencies, but yes, it gives you a few things that you might need. So 117. So I'll do L4 times 117. Okay, so now if I do a zoom, I'm going to turn this off. If I do a zoom, oh, there it is. If I go like the lobster claw, eventually I'll find it. I'm going to do a zoom 9 again to re-zoom our data. Okay, zoom 9. There it is. Oh, this is nice. It's like the flipping the bird distribution. Beautiful. I am going to change the window to make it a little bit better. I'm going to do a scale change to X scale of 1, X max of 11, just like before. 0, 1, 2, 3, up to now it looks like it should. I mean, it looks like it should, right? Window, make that be like 35. Oh, that's beautiful. So what you see, if you were to fit a bell curve to our data here, which it looks like a bell curve now, doesn't it? It's shifted to the right, isn't it? Which, once again, is evidence that perhaps we're doing better than guessing. But Lauren's like, but you haven't adjusted for sampling error. And she's right. We haven't adjusted for. All we know is the average of this curve is 5.5, right? So what do we have to do?
Hang on, going back to the fish, our little top of the other bell curve is in the tank. So
but here's the deal, where's the tank? That's the question. Where's the tank on the cumulative data now? We have to reform it, don't we? We have to make the tank again. Let's make the new tank, which is the cumulative data. Predict what the tank is going to look like. Predict what the tank is going to look like based on what you know about confidence intervals, the central limit theorem, and sample sizes increasing. Stat tests. T interval is already set up. This is where your data is, L1 and L2. We haven't changed. All we've changed is what was in NG. Again with the sound effect, please. Yes! Let's calculate it. Let it think. Average of 5.6, which I think ish is where our average was here. I think our average is a little bit higher, actually. A smidge higher. But look, it's 5.3 to 5.9. 7.5. 6.5. Cumulative.
Beautiful.
Why?
Why what?
Why did it get,
Because you had more data to look at.
Remember, the margin of error decreases with the sample size increasing. That's why, number one, as you do larger samples, the normal little variations in the sample are going to even out and makes Renee feel better because she's like, wait a minute, there's a hole in there, but not really. The hole is just random error. Thank you for that. Perfect. Perfect. But more importantly, the more samples we do, the closer, the better our precision gets in our estimate. So it looks like our p hat, or excuse me, our x bar was a little bit higher than the cumulative x bar. Again, random chance. Random chance, a few more bars on this side, pull it that way. But when you weight that with the other 100 and whatever it was, about 100 observations, you start to see where it's starting to settle in. Just like the penny spins. You guys had a very, very different result than the overriding cumulative result for the penny spins. Random chance. Random chance, all kinds of variables I can't control for. But there it is. And once again, if you compare it to 5, it looks like we're doing better than guessing, cumulatively. Whether 0.3, whether a minimum difference of 0.3 is meaningful is up for you to fist fight with friends over coffee. But it is a statistically significant increase. That's the thing. And now you open the can of worms. And you say, looks like the energy field can be sensed. And then you get a fist fight over coffee about, is that meaningful? And I don't want to push that back, but you can give them T interval. And you go, here you go. But this is stat class. Isn't that great? And we have Dr. Mark Eberly for science. Tell him. He loves this experiment. When I say love, I think he hates it. But he loves the dialogue it starts. The idea about random chance versus meaningful change. Yeah, good. Let's wrap this quiz up, because we just answered everything on the back, but we didn't do it in order. And thank you, because not doing it in order was actually a lot of fun. So, let's do it. Let's get the lights on. Let's kill this.